Hello, it's Stephen and Simon again, and
Hi.
we're at the end of the second week of the MOOC, and there's a lot of really great discussion still happening, which is really cool. And so we're just kind of making this video to go over, I guess, a few topics that we've seen come up in comment threads a couple of times, and maybe clarify a few things.
Yeah.
And so one of the first things that we've noticed is people talking a lot about appending and how it's slow, and maybe that you should, in particular, con stuff onto lists and then reverse them afterwards. And we just thought we might explain why that's slow, or what case that behavior happens, is that very slow behavior. So
Okay.
How does that?
Let's do
how does
that.
that happen?
Yeah. Okay. So one thing to start with is to say just how append is defined. So we define append by doing a recursion on the left. So we say that an empty list and y's is just y's, and if we join x cons x's to y's, that we get that by joining x to the result of consing x's and y's. So I've written there, I've written them as equations rather than as definitions, but you can see what the point is there. So in particular, you can see here that if you have a list which just has one element in it, and you join that to y's, that's just in one step is x cons y's. So really, it doesn't matter in writing a definition where you want to join a singleton to the front of a list, whether you write it as a direct cons or just as a singleton like that. But let's look at another example. So if we want to define reverse, we say reverse of an empty list is the empty list. Whoops. Incidentally, we thought it was quite nice to use a whiteboard rather than
Type it out. If you disagree, let us know.
reverse of x cons x's is, and what we do here is we reverse x's and then stick x at the end. As I've been arguing all the way through, this is a nice direct recursion. It says reverse of the empty list is the empty list, reverse of x cons x's, x is the head, first element, x is the rest, reverse the rest and stick x at the end. It's clearly reverse. But there's a problem with this. So if we reverse a list like 1, 2, 3, 4, the answer will look something like this. We're reversing 1, 2, 3, 4, we'll have an answer that looks something like this. Where we've got the plus plus are nested to the left. Now, plus plus is associative, it doesn't matter how you nest it, but we've created this leftward nesting. And let's think about how complex this definition is. If you look at the number of steps we have to take to resolve joining two lists together, it will be proportionate to the number of elements there are in the first list. Because there we do one step, and we've now got a recursion where we've got a list which is one shorter on the left. So in order to hit this bottom case, we've got to go through every element in that list, and so it's linear in the list on the left. Now with that insight in mind, we can say, okay, this is going to take approximately 2 steps, and now this is going to take approximately 3 steps, and then this whole thing is going to take approximately 4 steps. So we're getting an answer that looks like, more or less, the sum of the numbers from 1 up to n, and that is quadratic. So the naive reverse algorithm is quadratic.
But there's a nice little fix to this, right?
But there's a nice fix to it. So let's look at the fix. What we do is define a different function, and this function we call shunt, in honour of what people used to do in railroad yards. So what we do with shunt is we take 2 lists and we shunt the elements from the left-hand side onto the right-hand side, like this. And when we get to the end, when we've got nothing left on the front, we just return what we've got. Sorry, nothing left on the left-hand side, we just return what we had on the right. And you can see the effect of this is to take an element from the front of the list here, and what we do is make another call to shunt and put the element on the front of the other list. And you can see that if you just move back a second, we can see that if we do shunt of, I don't know, 2 on the front of 3 on the front of whatever, we step first of all to do a shunt of 3 on the front of, and then 2 cons y's, and that turns into another call to shunt on whatever is left with 3 on the front of 2 on the front of y's. The great thing about writing things on the whiteboard, I can write incorrect syntax and it works okay.
Yeah.
If I put a comma there, it would be correct. So let me do that.
Yeah.
So you can see the effect of this is to move those elements, and of course they get reversed as you do that. So we can say that reverse of x's is simply shunt from x's onto an empty list. So what we've got here is, you can see it's pretty straightforward to see that each cons in there turns into a cons in there, so it's a linear algorithm. So we reverse it in time, in a number of steps that's proportional to the length of the list.
And so this is the tail recursive definition of reverse.
Yeah.
And that leads us nicely into our next topic.
Yeah. So the first topic was, just to be clear, plus plus can be, when it produces left nested, plus plus is inefficient. But if you use it like this, if you use it as a shorthand for cons, it's not a problem.
Yeah.
But just remember that is just that shorthand. And what Stephen is saying here is that we're now using what we call a tail recursion to compute this function.
And so the key part that makes this tail recursive is that shunt is the call to shunt is all that's on the right-hand side of this definition, or the constant. And
well, in general, it's the last thing we do on that side.
That's true, yeah.
We only call shunt right at the end of that. We
Yeah.
might do some other stuff, but we call shunt right at the end. And the interesting thing then is that this looks very much like a loop. So what we're doing is we're saying, when our list on the left is empty, we just return the list on the right. Otherwise, what we do is take the element from the front of the first list, place it on the front of the second list, and loop. So we could write this as a while loop. While, let's say, x's doesn't equal the empty list, what do we do? Well, we replace x's, let me call it x's. We simultaneously replace x's and y's by, well, we replace x by the tail of x's and y's by head of x's stuck on the front of y's, cons y's. So simultaneously, each step we take an element off the front of the first list and put it onto the front of the second. Now, Erlang is nicer in that it allows us to do this sort of pattern match here. But you can see that instead of using head and tail here, perhaps it would be clearer if I wrote this as z's, and then we would not be confusing. If I write that as z's, and you can see that we're doing the pattern match of x, vertical bar x's, is matched to z's. So there we have head of z's is x, tail of z's is x's, and that's what we're doing. That's what we're doing in there. So what we've got is that while loop, and so I guess what we're doing when finally z is equal to the empty list, we're just returning y's, and that corresponds to this step. So you can see the looping behaviour we're getting from this recursive call, where, in fact, here all we do is change the values of these these variables. So we're treating each slot here like a variable, and in the recursive call, we're changing those values. So it's like a while loop that we see there.
Yep.
So is that about it? Is that all we wanted to say?
I think those are the big things.
There was something about just the efficiency of compiler optimizations and so on, but you replied to that in the in the video in the forum
discussions. Yeah.
So I think that's really all we wanted to say. I mean, well done for getting this far, and we look forward next week to talking in a bit more detail about higher order functions, so functions as data, and all the fun things you can do with those.
Yeah.
Good. Okay. So. And there will be a video, a feedback video at the end of the course, which will be at the end of next week. So there'll be one more of these, and hopefully we'll be letting you know about that through a particular email. Okay,
cool.
So that's it from us.
Yeah, keep up the good work.
Thanks very much.